So it's my pleasure to introduce you Stefano Bagnulo, who is our guest here this week. Stefano did his, I should know everything. Stefano did his studies in Florence, in Italy. Then he moved to Armagh, which is in Northern Ireland, for his PhD. After that, he moved to Vienna for a postdoc position at the university. Then he got the fellowship at ESO in Chile, where he moved then. And after the fellowship, he became an ESO staff. So he was a lot on the mountain at the big telescopes. And while he was there, he got a position back in Armagh, where he did his PhD. And that's where he is now a staff astronomer in Armagh. I know Stefano since many years. He's a great PhD supervisor, and that's where you say that I'm a great student.
PhD supervisor.
Yes, you're a top. What do you think of me then? Thank you. So Stefano is an expert in polarimetry of it. And he has done lots of work on polarimetry of the solar system bodies, but also of stars. And today he's going to talk about some of the work he's been doing on white dwarfs that I think connects to some of the stuff.
Thank you for the introduction. The title long enough. And I was told that I should talk a little bit about the polarization. And so forget for a while about the title of my talk. And in general, everything that breaks the symmetry in a radiative source, or between the radiative source and the observer, produces polarization. And for instance, the reflected light is polarized. And you can understand in physical terms, just in a naive way, thinking about an electron that is sitting at a surface, that is when it's hit by a radiation, is more free to oscillate in the direction parallel to the surface rather than going up and down. So we expect a polarization that is perpendicular to the scattering plane. And the nature of the polarization somewhat depends on the surface structure and composition. So polarimetry can be used as a diagnostic tool for instance, for asteroids or even exoplanets. And in case of asteroids, there's a well-established technique which consists of measuring a broadband polarization of an asteroid as a function of the phase angle. The phase angle is the angle between the sun, the target, and the observer. And you see that different asteroids have different curves, and because they have a different structure, in particular, all these curves have a different minimum and polarization and a different slope. And we see that the deeper is the minimum, or the steeper is the curve, the darker is the surface of the object. So polarimetry can be used as an immediate, as a very simple diagnostic tool to measure the albedo of an asteroid. And this is quite important because with the photometry alone, you cannot distinguish a big and dark asteroid from a small and bright one that could have deep consequences in case of an impact on Earth. And that's why, for instance, ESA is paying us to monitor some near-Earth objects in a polarimetric mode. Not that we think that we will save planet Earth, but we are doing this exercise. In polarimetry, we can also distinguish organic from non-organic material. This is the polarization of a liver. I don't know if any of you has been on ÖAW Observatory at ESO in Chile. This plant was taken from the Residencia in Chile, and then we use it to stuff the polarimetric unit of an old instrument called the EFOSC. That's maybe some of you have used. And we obtain a polarimetric measurements of this is spectropolarimetry of the leaf. So I can confidently say that if an asteroid was covered by a forest, we will be able to detect it with the polarimetric techniques. Circular polarization is also interesting because of the chirality of organic material. You can distinguish an artificial grass from a real vegetation in circular polarimetric mode. Because organic material shows a signal of circular polarization. So in principle, you could use a circular polarization to detect extraterrestrial life, in principle. And you can measure the pollution on Earth with the polarimetric technique. In general, polarimetry is sensitive to the aerosols on the sky, and perhaps more interesting for you, can be used to characterize the atmosphere of planets, including exosolar planets. And Daphne Stam, I think, was among the first one who calculated how the polarization of detected from a terrestrial-like Earth-like planet would appear. And when we observed the Earthshine, we got exactly the same feature that we have seen in the theoretical models. So we can detect oxygen and water in polarimetric mode, if only we have the photons to do that. This is polarization from scattering that is probably more relevant to the large majority of you. Another source of that breaks the symmetry. So another possible explanation for the observed polarization is the presence of a magnetic field in the atmosphere of a star. And you might be familiar with the Zeeman effect, and the technical way to explain this slide is to say that the magnetic field can be detected and studied through the analysis of the Stokes profiles of spectral lines. So the Zeeman effect is also the corresponding effect is seen in spectroscopy and in spectropolarimetry. So a line formed in the presence of a magnetic field will tend to split in various components. The classical interpretation of the Zeeman effect was based on a Zeeman triplet. And so the splitting is proportional to the field strength. The line will be also polarized. In the presence of a magnetic field that is transverse to the line of sight, is perpendicular to the line of sight, we will see a spectral line that is fully linearly polarized. While circular polarization is sensitive to the longitudinal component of the magnetic field. So in general, field strength is affected intensity spectrum that was observed with normal spectroscopy, and is also producing a signal of polarization. Here we have a theoretical profile of a very deep spectral line. We have on the top left panel, we have a Stokes eye, and then without a magnetic field, there is no circular nor linear polarization. And then we introduce a magnetic field. Here I consider a certain orientation with respect to the line of sight, and the intensity spectrum will be split. The line observed with normal spectroscopic techniques will appear split into three components that are circularly polarized and also linearly polarized. This is the theory of the Zeeman effect. I mean, these are the theoretical predictions. When you observe a star, the situation is much more complicated than that because you integrate on a stellar surface, and the magnetic field will have different orientations in different regions of the stellar surface. So the signal will tend to cancel out, and so will tend to be weak, but still detectable in many cases. Here we have, for instance, a situation, I represent a star with a dipolar field that is frozen at the stellar surface and tilted at a certain angle with respect to the stellar, with the rotation axis of the star. And you see that as the star rotates, the shape of the Stokes profiles on the left changes. We have Stokes I on the top left panel and Stokes V on the right upper panel. Linear polarization is generally quite weak. We don't observe much of linear polarization to detect stellar magnetic fields. And okay, this is my introduction to the phenomena that produce polarization. And I will move now into the subject of this talk, and which is not far away, as my a priori think, to exoplanetary, to the interest of exoplanetary science. So I will talk about white dwarfs and about their magnetic fields, and then at the end we will talk about exoplanets again. You may remember that 95% of stars ended their life in the form of a white dwarf. A white dwarf is an object that has retained a mass comparable to that of the sun. The average mass of a white dwarf is 0.6 solar masses, but with the size of comparable to that of planet Earth. So there's a very huge density that creates a situation of a state of a degenerate state in the matter, but also makes the white dwarf quite faint. And in fact, only a few white dwarfs were known in the last century. Now, thanks to Gaia, we know about 250,000 white dwarfs, and we have also classified photometrically. So the field has expanded a lot thanks to the Gaia mission. Some of these, or many of these white dwarfs have a strong magnetic field. The order of magnitude is between a few tens of kilogauss and several hundred gauss. And just to associate this number to something more familiar to you, I put together this table that summarized that the strengths of the magnetic field in things that are common in life, like the Earth magnetic field, is of the order of 1 Gauss. If you have one of these magnet or in your refrigerator, the magnetic field is the sunspots have a field strength between 1 and 3 kilogauss. Anyway, the order of magnitude is 1 kilogauss. With the 10 kilogauss, you can erase your credit card. And if you wonder how to do it, you can take a transformer, 50 kilohertz transformer, and put your credit card inside. The credit card will be erased. It's all your debts. Or you can send your credit card on the surface of one of the chemical peculiar stars, some of which have a magnetic field up to 30 kilogauss. Many of them are weaker, but chemically peculiar stars of the upper main sequence are the objects outside of the solar system where the magnetic field is best studied and detected and studied. And Luca is also an expert on this. If you want to levitate a frog, you need a 160 kilogauss field. And this experiment has been done and has been awarded with the Ig Nobel Prize in 2010 to the same guy that in 2016 won the Nobel Prize for Physics for the research on graphene.
And his memory was also erased.
Now it's credit card.
But why does it float?
Because it's magnetic composition of the frog. I don't know why a frog and not something else. In the laboratory, we can create a magnetic field of the order of 10 megagauss. I was told recently that people can reach higher than that. So perhaps this is a little bit outdated. But anyway, you want to compare with the magnetic field of white dwarfs that goes almost to 1 gigagauss. Let's look now to example of a white dwarf spectrum. And here with the solid line at the top, I show the Stokes I spectrum, or the normal spectrum that you would obtain with a spectrograph. And you see normal spectral lines. They look, it's low resolution, but they don't look very. But actually, if you take a spectropolarimeter, and you observe them in a circular polarimetric mode, you see that these lines are polarized. So spectropolarimetry is in general a very sensitive tool to measure magnetic fields that are revealed when spectroscopy doesn't reveal anything. Here is another example of two calcium line in a white dwarf that appear normal calcium line in intensity, but they are strongly polarized. Then when the magnetic field is strong, you start to see, even in white dwarfs, the Balmer lines of white dwarfs are quite broadened by pressure. So you need a very strong field to start to see a splitting. And you do see them splitting in white dwarfs, and you see also then that they are circularly polarized. But the Zeeman effect is not enough to, by no means is enough to study white dwarfs. The white dwarfs have magnetic fields that are much stronger than what can be dealt with in the Zeeman regime. Because when the field becomes of the order of several tens of megagauss, then it becomes comparable to the Coulomb force. And then the continuums start to be polarized, and the lines go everywhere in the spectrum. You need a numerical calculation to know where they go. And when you do them, you find yourself to deal with this spaghetti diagram, which shows the component of the various Balmer lines, the position of the components of the various Balmer lines as the field strength increase in the y-axis. So with a magnetic field as strong as those we find in certain white dwarfs, you find the component of H alpha in the ultraviolet, and component of the red component of the sigma component of H beta in the infrared. So the spectrum can be completely crazy. And here I show you a spectrum of a non-magnetic white dwarf of a certain temperature. And with the blue line, I show the spectrum of a star that has the same temperature and mass, but with a 300 megagauss magnetic field at the surface. And you can see that the spectrum becomes totally different than what you would have without a magnetic field. Just to give you an idea, this is a sigma component of H alpha, and that is a sigma component of H beta. And the spectrum, the circular polarization spectrum of this star is also interesting. There are some featureless white dwarfs. The white dwarfs, what a white dwarf does during her life, or its life, I don't know, its life maybe. A white dwarf just cools down. Apparently not much happens. I mean, there are no production of energies in a white dwarf. So they cool down with the time in a way that may be more or less complicated by phenomena of, for instance, core crystallization. At some stage, they are so cooled that they don't produce any more spectral lines. And this is also quite interesting for a reason that I will discuss later. And so when you don't have spectral lines, it's very difficult to detect any magnetic splitting. You cannot detect line splitting when there are no lines, but circular polarization is still able to detect a magnetic field, even in featureless white dwarfs. This is the spectrum of white dwarfs. That the blue line shows the spectrum, the intensity spectrum of a white dwarf, and all the features are the telluric lines and then maybe some CCD faults. Circular polarization is there that tells the magnetic that this star has a strong magnetic field. The other very important aspect is that only with polarimetry you can get information about the morphology of the magnetic field. And I will come back to this point at the end. Here in the top panel, I show Stokes I with us given normal spectrum of H alpha of a star observed at different times in basically sampling two different places of the position and time of the stellar rotational phases. The bottom panel has Stokes V with blue and red line, and you see that they are flipped. They are flipped because in the meantime the star has rotated, and before we were looking at the positive magnetic pole, and now we are looking with the red line at the negative magnetic pole. So while stocks, the intensity spectra are quite similar to each other. So it's only with the polarimetry that we obtain information about the morphology of the magnetic field. Now I will, in the next 15 minutes, I will 10-15 minutes, I will talk about something related only to the to stellar astrophysics. What is the origin of these magnetic fields? And then I will go to interaction between these magnetic fields and the exoplanets. So what is the possible origin of the magnetic field? In stars, we know of two mechanisms. One is the dynamo mechanism, a contemporary dynamo, like in the sun. There are currents inside the sun that run and create a magnetic field. In chemically peculiar stars, instead, as an example, we observe the remnant of a magnetic field that was formed in a previous stage of the stellar life. So we call those fossil fields. They are there and just decay with time, with a very long time scale. And they are formed perhaps when the star was in the Premian sequence, or anyway, in a previous stage of the stellar life. And so the question, of course, is to answer is whether the origin of the magnetic field in white dwarfs is a fossil or a dynamo. And what the observations tell us about these fields. So first of all, observation tells us that the magnetic field of a white dwarf has nothing to do with the magnetic morphology of the sun, because a magnetic morphology like the solar-like stars would have a zero signal of polarization. Because if you have sunspots, you have a negative pole and a positive pole on the same stellar, on the same hemisphere, and the signal cancel out. So the simple fact that we observe a non-zero signal of circular polarization tells us that the magnetic field in white dwarfs is organized at a large scale, like a dipolar field, like we have seen in the previous animation. And the fact that it is sometimes variable, I will come back later on this point, tells us that the fields are often not symmetric about the rotational axis. So we are in a situation like this. So we have a star that it rotates and show different aspects of the magnetic morphology to the observer. The next step is that what the observation tells us when we try to correlate them with a certain stellar parameters, for instance, the mass or the temperature, which is in case of stars and white dwarfs is the same as time. Temperature equal to time is a bit strange, but because the temperature decreases with time, we associate the temperature of a star, of a white dwarf, to its age, cooling age. Okay, a white dwarf never starts to be hotter, just goes down. So the idea that we had few years ago was to do a spectropolarimetric survey of the stars within 20 parsec of the sun, try to sample all of them to avoid a bias introduced by the so-called magnitude-limited surveys. Because with the magnitude-limited survey, what we observe are only the brightest white dwarfs, so only the youngest white dwarfs. It's only when we decided that our target selection will be based on volume selection criterion, that we sample a population that is representative of the real population of the white dwarfs. And this was possible mainly thanks to Gaia, because Gaia found all the white dwarfs around us with a very accurate distance, and also because of the photometry of Gaia, and thanks to the modeling work made mainly by people in Montreal, that we are able to assign to each white dwarf a temperature and a mass, and with the cooling models, age and a mass. So we are able to populate this diagram that has in the x-axis the cooling age and in the y-axis the mass. And then what we are going to do now is to populate this diagram with the little dots that represent all the white dwarfs within 20 parsec from the sun. And this is the result. Let me explain what these symbols mean. So a solid symbol represents a magnetic white dwarf, and an empty symbol represents a non-magnetic white dwarf. So a white dwarf that we have observed with spectropolarimetric techniques, and we have detected nothing. So it's quite accurate, not perfect, but certainly much more accurate than what you would obtain with the spectroscopic techniques. The color is a bit irrelevant in this context. They represented the composition of the stellar atmosphere, but we didn't find any correlation. It's there for historical reason because I was too lazy to change the plot. But it's not. Is just forget in this the meaning of this symbol, of this color. And then larger symbols represent a stronger field than a smaller symbol. So what we see here immediately is that the large majority of ultramassive and young white dwarfs have a strong magnetic field. 7 out of 8 white dwarfs that have a mass higher than 1.045 solar masses have a strong magnetic field. You go down, it is the diagram, and you look at the so-called normal mass white dwarfs, and you find very few magnetic white dwarfs. Only 2.5% of young white dwarfs have a magnetic field. When young, I mean up to 2 or 3 giga year. And then you look at the old average mass white dwarfs, and you find that 25% of them have a strong magnetic field. So this is the result of a volume limited survey, and it wouldn't appear at all just picking up data from the literature, because literature data are affected by strong biases due to field detection techniques and target selection. So let's give a physical interpretation here. We know that the ultramassive white dwarfs that have a mass typically 1.1 to 1.3 solar masses, they are the product of merging. 2 binary white dwarfs is a white dwarfs merge. So the idea is that when they merge, they rotate orbit very quickly, and they produce a dynamo that immediately becomes responsible for extremely strong magnetic field. Here, instead, we see that a magnetic field that emerges at the stellar surface with the time. So the star is born as non-magnetic, and with magnetic, with time it becomes magnetic. So the idea is that there's a magnetic field buried at the core of the star that was formed in a previous stage of the stellar evolution, that then comes to the surface with the time and then becomes bigger and bigger with time. This will be the emerging magnetic fields. And according to this interpretation, all these fields would be of fossil origin. Now, this is my favorite interpretation at the moment, but I also, well, we also, this work was made mainly by myself and John Lansstreet. And so far we have been looking at, we have tried to look at patterns dividing this diagram with vertical and horizontal lines. Let's put a oblique line here. These lines show the time at which white dwarfs of a certain mass start the core crystallization. And you see that the magnetic field becomes much more frequent after the stage of core crystallization has started. And in fact, there are theoretical predictions that says that core crystallization, because when the star becomes cooler and cooler, the core starts to become solid, basically. So this solidification or crystallization of the core produces an instability in the mantle around the core that joined to fast rotation would create a dynamo responsible for a magnetic field. And that would be a beautiful verification of this theory, except that the theory struggles to justify fields so strong as we observe. I think that the theory is comfortable up to 1 megagauss, not much more than that. And plus you see stars that are magnetic well before crystallization. So the field is still open. And there are all other criticisms to this theory because even if the dynamo were sufficiently strong to generate the field that we observe, the field would take a long time before coming to the surface. So we will see. I mean, the field is continuously evolving, and maybe people will come with better ideas in the future. So this is the idea of the dynamo idea. I will just talk about the variability of magnetic wide dwarfs, because it is a result that is of basically no interest for you, but it's very nice for me, so I wanted to tell you. So you know that the wide dwarfs are, many of them are considered flux calibrators. They are so stable that can be used to calibrate our fluxes. So it's very difficult to measure their rotational period, except when they have a magnetic, when they pulsate or when they have a magnetic field. So rotation of a wide dwarfs may be probed by magnetic variability. And here we have a clear example of there's a time series of Stokes I profiles in the top and Stokes V profiles at the bottom. This is the same star that has been repeatedly observed and show Stokes V variability. When you measure the variability of Stokes V, you measure the rotational period of the wide dwarfs. As simple as that. Here you have another example. This is a much stronger, a wide dwarf with a much stronger field that rotates very fast. And you see with the time, the spectrum changes. More interesting is the situation about the non-variability of some magnetic wide dwarfs that have been discovered already in the 70s. It was discovered that some wide dwarfs show very little or no variability when observed in circular polarization. And the interpretation has been classically given in terms of a slow rotator. So people thought that the star loses angular momentum due to the friction of the magnetic field with the gravitation, with the polar emission. So we had this idea that some wide dwarfs are very slow rotators. And John Lanslet and I wrote even a paper talking about modeling one of these extremely slow rotating wide dwarfs. Then we started to look at more statistically, in a more statistical way, to all of these wide dwarfs that don't rotate. And we found that we compiled a long list of stars for which we have observations taken in the course of years. John Lanslet started to observe in the early 70s, and he had in his drawer, he has some plots, handwritten plots of polarimetric observations of white dwarfs that had never published. And we used also those to compare with the modern observation. And we found many white dwarfs that don't change at all in spectropolarimetric mode. And we created this diagram. Well, this time the red points are relevant. In this plot, I put with the red dots white dwarfs that show no or little variability. And blue dots show white dwarfs that show variability. And the size of the symbol again represents is proportional to the field strength. And you can see that strongly magnetic and old white dwarfs tended to be not variable. Everything else is variable, particularly all weakly magnetic white dwarfs are variable, and all young magnetic white dwarfs are variable. So the idea, okay, we have discovered that indeed the magnetic field is stopping the star, is slowing down the star. Except that it can't be like that. At least we don't think that is possible, because First of all, theoretically, it's not clear how the magnetic field can spin down a star to stopping it. Second, we observe these blue dots have a rotational period of hours, minutes, hours, days, 2 weeks at most. And then suddenly we find the stars that don't rotate. So there's a gap. It's not like, for instance, for chemically peculiar stars where we know that they are slow rotating stars, but there's a distribution of the rotational period. Here, there's nothing. Either they rotate relatively fast or they don't rotate. So our interpretation is in terms of actually that the magnet is this one. Okay, first of all, this was wrong. Forget about that. We cannot. And that's the interpretation that we have now. But the reason why they don't show polarimetric variability is because the magnetic field tends to align to the rotation axis when the magnetic field is strong. And why would do that? Well, because the magnetic field tends to change the shape of the star. The magnetic, because of the Lorentz force, the magnetic stars tend to be a little bit oblate. And so the star suddenly start to rotate around an axis that is not this principal inertia axis. And then because of, stability, question of the stability, what happens also in asteroids, the two axes will tend to align, except that it's not the rotation axis that changes inclination, is the magnetic field that reaches the rotational axis. So this is our idea, and I think we proved wrong. And now I go to the interaction of magnetic white dwarfs with their circumstellar environment. I told you, well, you know that white dwarfs are extremely dense. They have an extremely strong gravity. And because of that, what you see, what is left at the surface is only the lightest element. Everything else, things you can see only one element, sometimes two. And here, for instance, is an example of a hydrogen-rich white dwarfs, and you see only Balmer lines. Then, when the stars is cooler than 11,000, helium lines are no longer visible, and below 5,000 Kelvin, you don't see hydrogen lines. You see a featureless white dwarf. Okay, except that sometimes you look at things like that, you find things like that. So this is a spectrum of a white dwarf with a lot of metal lines. I didn't put labels, but you can recognize calcium there. Then there's iron, magnesium, manganese. And for many years, this was considered an enigma. Why certain white dwarfs show metal? They shouldn't be there. And some theory explained in terms of interaction with the interstellar medium. And finally, it was understood that these are the debris of an exoplanetary system that are basically falling at the surface of the star. And they stay there not for long, but long enough to see them and to measure them. So maybe 1 million, it depends on the physics of the stellar atmosphere, but it could be 1 million years or sometimes less. You're familiar with this. The first exoplanet was observed in 1997, right? The first time a human being detected an exoplanet. Wrong. The first time we observed an exoplanet, well, or at least something belonging, it was in 1917. That's the spectrum of the first white dwarfs that was where calcium lines were detected. So this was the first detection of not really an exoplanet, but the bulk of and here is the contact with what many of you are interested in. You cannot see anything more suitable than a chemical abundance analysis of a white dwarf to study the composition of the bulk of the exoplanetary system. Because you have it here. Just ask your colleagues who do abundance analysis to measure this, and you not so simple. But that's you will never get the spectrum of the core of a planet if you don't look at white dwarfs. And you know that some of these white dwarfs are magnetic field, and this is quite interesting because, okay, I show you already this plot. These are the calcium line that appear polarized because of the presence of a magnetic field. And just a couple of years ago, 2024, yes, it's 2 years ago. Well, I mean, 2 years ago was the publication. We discovered that one of these, this is one of these metal polluted white dwarfs that was showing line variability as a function of time, periodic line variability. So the star rotates and we see line becoming stronger and weaker, stronger and weaker. And this variability of the line is synchronized with the longitudinal magnetic field, with circular polarization. Circular polarization is sensitive to the longitudinal component of the magnetic field. And so we noticed that when the magnetic field was stronger, the lines were stronger. And when the magnetic field was weaker, the line were weaker. So when you have a longitudinal field equal to 0, it means perhaps like you have a dipole still seen equator orb, and when the longitudinal magnetic field is maximum, you have you are looking at dipole on a pole on. And we observe the same thing in another white dwarfs, 2138, the -332. See again, the lines observed at different epochs, they change variability. And here I show something better. I show the variation of the longitudinal magnetic field as a function of the rotational phase. And you see that it's synchronized with the variability of the equivalent width of the lines. And the interpretation here, it's simple, I think. It's that we are looking at metal abundance spots or patches at the magnetic poles of the star. So the accretion of these two metal polluted white dwarfs happens through the linear force of the magnetic field. The cannibal star, we call it, in a press release. So the cannibal star that is using the magnetic field to capture debris of the stellar disk. The question is, of course, how can we capture? Because to have an effective magnetic field, you need to ionize the material. What is your ionizing the material? That is sublimating, but there's not energy enough there's no radiation from the star to ionize the material. The star is very cool. John Lastrit came with the idea that you have enough energy to ionize at least some of the elements. And then as soon as you start to ionize something, that element, that atoms, change its trajectory, and the other fellow atoms smash against it and becomes ionized by collision. And then they go down and create a chain of a collision and ionization. That's appearing roughly supported by numerical calculation, but roughly, not just a good idea. These stars also show a light variability. With a solid line, I show the test light curve. The star is dimmer when the magnetic field is stronger. And I just tell you that we don't know why. I mean, some people think they know it, but they don't. I mean, the part is that people try to apply the same physics of AP stars into white dwarfs, but the physics is different. It's not clear yet. It's, I mean, if you are familiar with the making the surface more opaque, and so the light curve goes down. The problem is that it goes down in all filters, so there's no way that the light goes out. So it's not a line blocking effect. And so far, I think we have not understood why. It is actually would be interesting to investigate that. And I think that I finished now.
what you're showing about the white dwarf seems to be very related to the orientation, I mean, field effect rotation. And in your graph, you had a lot of white dwarfs which didn't show any magnetic signature. What is the percentage of them which could have, but you would not detect them because
It's very high. Yeah, yeah. You pick up exactly the point that I have in mind, and it's very, very good. Yeah. I think that many times you don't see variability in metal polluted white dwarfs if they are magnetic, because the magnetic field is aligned to the rotation axis. And so the configuration never changes to the observer. But when the magnetic field is weak, then the field is not aligned, and we do see and I can't anticipate that 3 out of 4 magnetic DZ white dwarfs, DZ is metal polluted, show line variability, weak field and line variability. 3 out of 4. And it's well, it's not a strong statistics, honestly, but it's still 3 out of 4. I mean, there's an indication that the variability is common. And when it's not found, the equivalent with variability is because the field is aligned to the different axis.
And on your last slide, for the dimming of the star, when the magnetic field is stronger towards the observer, I mean, in the sun, you see this, like when you have a strong magnetic field, the photosphere is darker.
Yeah, but
anything?
No, it's anything like that. No, I don't think so.
So the surface
You don't see something. There's no convection that brings cooler material from down.
I see. Okay.
But that's really that's an excellent explanation. First guess is that one.
Yeah, thanks. Very interesting talk. But could you make a 3-parameter plot for the white dwarfs, which you can measure the magnetic field and the rotation period and this cooling age that you were showing, so that
I could, yeah, not now, but yeah.
yeah, no, not now, but do you think that would give another distribution about the strength, both related to age and rotational rate and things like that?
It could. The problem is that we don't know many. Well, we start to know now some of the rotational period, but it's yeah. Well, I would say the simple answer is it's worth to try. Yeah, yeah, it's worth to try. But yeah, I think the other aspect that I would like to plot as a third axis maybe is the inclination, the variability itself rather than the period. So because I would like to see that this tilt axis between the magnetic field becomes smaller with age. So that the time I would like to see the star aligning with the time.
Could you maybe speculate a little bit about future facilities, maybe ELT, HWO, or whatever? Yeah. Will it ever be possible to say something about the magnetic field of an exoplanet? I mean, not the central star of the exoplanet system, but the planet itself?
I think it's possible. I'm not able to do. I mean, this is a science case for polarimetric capabilities of the larger telescopes, no doubt.
I mean, polarimetry is one thing that could also be, you know, just like the reflection. You don't need magnetic fields for that.
No.
I think that's very interesting. I just wonder when you have actual imprint of magnetic field, because you know, maybe you need some magnetic field to make a planet habitable, etc.
Yeah, you need it to protect it from the radiation. Yeah, absolutely. No, this is actually a quite active field. But yeah, the problem is we need the photons, and to get photons we need the big mirror and with polarimetric capabilities, and the ELT is not built in a way that you can easily put a polarimeter there. So I wouldn't be able to do right now quantify exactly how much. maybe you might know more of it about, I think that, I don't remember, has been working on that, it was a French, well, I wonder whether you know more about the interaction between magnetic fields of a planet and.
It's a long story.
It's a lot.
I have a question about coming back to your blocks with the core crystallization.
Uh-huh.
Can you say a little bit more? I'm a little bit, I mean, A, it's curious, and then the B is where does the, yeah, how would the magnetic field then?
So, okay, this is on the x-axis you have the time. So the star becomes cooler and cooler. And when it meets, so the star diagram evolves in horizontal lines because it doesn't lose mass.
Mhm.
Okay, so at some stage becomes cool and the core start to crystallize. The crystallization creates an instability in the mantle around. I think probably I don't remember exactly the reason of this. The reason why it is, I think, is an Helmholtz instability that is created just around. Yeah, I think it's due to some movement of elements that crystallize before and after, so that they sink and when they crystallize. And this movement creates an instability, and this instability joined to the fast rotation creates a dynamo. And the original article that it was hypothesized several times, but there's a paper by Isern et al. In 2017 that predicted field up to 1 megagauss. But we observed 300, 800 megagauss. Then the other researcher came and say, oh, well, but actually you don't need this. I mean, the dynamo effect is much stronger. And other people say, no, it's not, it cannot be much stronger. And so there is basically a debate on whether the crystallization dynamo would work or not. Observational is both at the same time very strong and tells us anyway that for sure there is something else because we know of young magnetic white dwarfs.
One question here.
Hi.
Yeah.
Can you show us the plot with the best light curves?
With the what?
The best light curve.
Yeah.
The last one.
No. No.
Yes. Yeah, you mentioned that the magnetic field affects also the shape of the white dwarf.
Well, this is a weak field. You see, the longitudinal field is 10 kilogauss.
But the total can be still high.
You could, yeah.
And the geometry of the white dwarf, can it affect the flux?
No, I don't think so. No. I mean, maybe I should be more precise. Why? Not say no, but
A few more questions.
we would observe it frequently if that was the case. We know many white dwarfs that don't have any variability, light variability, but they have a field stronger than that.
But if the equivalent width of all the lines, maybe not all, but of some lines change, wouldn't that have an imprint on the temperature structure?
Yes, exactly. On the emerging flux, basically, it would block the temp. It would block, and then yeah, I don't know whether the temperature would change, but probably yes. But the point is that you would see the flux coming from somewhere else. If you block the blue, you see the flux in the red, and that's actually a well-known phenomenon in AP stars. You see the colors in counter phase.
Well, it's probably more like in the wings and in the center of lines. So if you have broader lines, you might, well, if you have very narrow line, it's just say the Rosand opacity would actually decrease, and that would probably have an effect on the
total opacity.
Yes.
Could be. I don't know whether it's from the quantitative point of view would work, but let's say the classical interpretation is that okay, you block the light and the light comes from the fat, and this doesn't work. What you're telling is actually something different. Is needs more computation.
Here.
Yeah, okay, sorry.
Maybe a bit of a technical question. So you made the classification between magnetic and non-magnetic white dwarfs. What exactly is the criteria to classify it? Where's the threshold?
Yes, it's very simple. If you detect it, it's magnetic. If you don't detect it, it's not.
So this actually leads to my second question: is what is the resolution of magnetic field?
Yes, yeah, it's a perfect reasonable question to ask, and we have actually I removed some slides about this, but so if the star is young and well, relatively bright, but if it's young, it's hot, it has a line that within a certain temperature range is very deep. We have a sensitivity up to, I would say, 1 kilogauss normally. And then when the star is cold, old and therefore cold, the line are much weaker. The star itself is fainter. Our sensitivity becomes 2-3 kilogauss. No, more than that. Depends about 10 kilogauss, 20 kilogauss could be also. And then in stars that are featureless, in which we can measure only polarization in the continuum, is megagauss. We need at least 5-10 megagauss to see something. The trend that we observe is that magnetic fields are much more common in older white dwarfs, where it's more difficult to detect the field. So it's true that there is a bias introduced by our techniques, but the bias would, the bias in our data would be given even more emphasis to this trend that magnetic fields become more frequent when the star become older.
Okay, thank you.
Okay.
Thank you for the nice talk. I have a simple question. Do we know how the polarization properties of the signals propagating from distant stars to Earth observer are conserved?
Well, these stars are 20 parsecs. They are around the corner. So I think that I guess you wonder whether there's interaction with the interstellar medium.
Yeah, sure.
Yeah. I mean, we have this somewhat under control because we would see, for instance, if there's a linear polarization, because interstellar medium manifests itself mainly in linear polarization. It is a problem I didn't even consider because we are doing a local survey. In circular polarization, yeah, there could be certainly some effect of basically crosstalk between linear. I mean, if circular polarization eats something that a dust grain, it's like the earth shine, for instance, the light that is polarized by when we studied the earth shine, we were to take into account the polarization introduced by the scattering from the lunar surface. Now, with the interstellar medium, is not reflection, is a transmission. I think this application is negligible.
Yeah, you're also forgetting our first work. Many white dwarfs are used as polarization standard stars. In linear polarization, you see absolutely nothing. It's flat, and they are same distance, and you don't see any limit.
Regarding this core crystallization, you mentioned that the one which have high mass, they might be from merger. And my question would be, would then they would follow the same cooling age process? Okay.
I don't know, because there's a feature that I didn't find.
Because of course the curve is with respect to mass, but if the higher mass are not created the same way, would they follow?
How many old white? How many old ultramassive white dwarfs you see in this plot?
Yeah, there is none of them. Yeah.
No, yeah. I don't know where they are.
Okay.
I mean, with this, I don't know. I mean, there are two theories. One is okay, the white dwarfs, the merging product is a born again star, okay, because you have two white dwarfs that merge and start from scratch in these coolings. So maybe we are not old enough to see all the merging products. That's one possibility. The other possibility is also that actually these stars are much older than because inside the crystallization is actually slowing down the cooling down. I would say. It's slowing the cooling process. It's like because of the heat is absorbed by the solid crystallization process. So the star is actually what we are observing there is actually much older than. So the answer to your question, I don't know.
Thanks, Stefano, again.